Okay, hi everyone. Welcome to lecture 16. So we have seen, last lecture we introduced a new model of probabilistic proof called interactive oracle proofs. That one, that model put together the distinct features of interactive proofs in PCPs, specifically interaction and query access to proofs, so that we obtain a sort of a notion of interactive proof where in every round the prover sends an oracle rather than just a message. And so kind of played around a little bit with that model. In particular, we saw how that model still leads to interactive arguments using this commit then reveal, locally reveal paradigm. And we also went back to the PCP for n time, and we saw with basically almost no work, just by not unrolling the sum checks in the construction, we obtain a much more efficient sort of a proof system. In particular, we saw how to achieve these asymptotics. Okay, so almost linear proof length with some trade-off on the query complexity. Okay, and but the question is, we kind of really underused the model last time. We sent an oracle just in the first message, and we didn't really try hard to think of anything. So what we'll see today is that we're gonna start exploring how to obtain a linear proof length. Okay, this will primarily be for computations over large fields, and I think if we get to it later in the course, we'll see also how to achieve linear proof length for Boolean computations. When you start getting to these rather demanding notions like linear proof length, which specific type of computation you're considering now actually starts mattering a lot. Okay, so the goal for today will be to go back to some NP-complete language, arithmetic one, and specifically we'll focus on rank 1 constraint satisfaction. We've seen this before once. It was when we discussed linear PCPs. We saw two constructions of a linear PCP. One was for quadratic equations, and one was for a restriction of quadratic equations given by these expressions. Okay, so if you remember, you have these coefficient matrices which define this system of equations, which is just basically a bunch of quadratic equations that look like inner product times inner product equals inner product. Okay, so this was this rank one constraint satisfaction. It's not inherent that we need to look at rank 1 constraint satisfaction, just a little bit easier. Whatever I discussed today also holds for just normal quadratic equations over a field. And today, and I guess part of next lecture, we'll prove the following theorem, that for any field f that is both large and smooth, we'll see later what this means, but roughly large means that it should grow with the instance size. Okay, so if you have some computation of size n, you want the field to be of size at least order of n. And smooth, it will not come up concretely today, but it will basically be imposed by some sort of low degree test. It means that you have a subgroup that kind of whose order has many factors. Think about this as basically FFT friendly. Okay, that's basically the same type of conditions. Okay, and what's the key feature that we'll achieve today is linear proof length right here. Okay, so we'll achieve a proof length that it grows. So here we have two parameters. We have m and n. M is always at least, let's say, n over 3, otherwise you can discard variables. So really the dominating term here is m. So the proof length here grows with the number of equations that we're proving. Okay, the query complexity will be logarithmic, randomness as well. Round complexity will be logarithmic as well. And so that's the regime that we want to achieve. So this would be the first linear proof length that we see in this course. It is specifically for arithmetic computations because, again, this field f of the language is also the field f over which we're going to be expressing things, and it needs to grow with the instance size. Note that we cannot conclude that all of NP has linear size proofs also, okay? But because just moving between different NP-complete languages introduces overheads. NP completeness is a robust notion under polynomial time reductions. And in fact, this is not a theorem, but empirically, or at least almost everything that you can touch has quasi-linear time reductions to one another, okay? So if you don't care about polylog factors, then basically all of NP-complete languages still reduce to one another. But when you start caring about whether it is a quasi-linear reduction or not, or a linear reduction, then it's not the case. You can just always expect a linear reduction from one problem to another. So in the linear proof regime, it matters which problem you want to aim for, and more generally, kind of more expressive problems are better if you can prove linear size proofs for them. Is this point clear? Again, before, at the level of granularity at which we were stating results, we could just say, oh, an entire class has proofs with these parameters. Why? Because you focus on some complete problem for the class, and you rely on NP reduction, on reductions that are complete for that class to kind of reduce everything to that. In the regime of linear proofs, you don't necessarily expect that. At best, you can conclude that you will get the proof length is linear in whatever is the instance size that the reduction gave you. Okay, and I'm telling you, but I'm not proving that basically almost everything can be reduced in quasi-linear time. Linear time, that's a different story. Okay. And the quasi-linear time reductions are non-trivial. There were papers written in the late 80s, early 90s, basically showing that complexity theory is basically robust under quasi-linear time reductions. Okay, so that is the goal for today. Are there any questions about the goal or how it relates to what we did last time? Okay, so if not, let's go ahead. And from now on, we'll assume for simplicity that the number of equations equals the number of variables. This is not necessary. It will just, we already have enough notation as is, okay? But everything I say today can be done without assuming this, okay? And also just generally, you don't really expect, the type of instances that you get from NP completeness or reducing from circuit set, for instance, have M roughly order of n, though, it is also interesting sometimes to look at dense, sort of more unbalanced situations where you have a bunch of constraints. Anyways, so before we kind of get to the what to do for this linear size regime, it would probably be helpful to kind of take a step back and sort of see what kinds of encodings we've used in the past, because they're going to help us suggest what encoding we should consider to go for to achieve linear size proofs. So our recipe to construct PCPs so far has been to basically set the PCP to be made up of two parts. One is some alleged encoding of a candidate assignment. Okay, so it is some assignment written according to some format. So there is some encoding procedure that, it's not all strings are valid encodings, only some of them are, okay? An assignment needs to be kind of encoded that way, and it belongs to some special set of specially formatted strings, okay? And then we had some sort of auxiliary a proof of satisfiability such that if indeed the first part of the PCP is reasonably close to some valid encoding, then, by leveraging the second part of the PCP, we can establish that whatever kind of message was encoded does satisfy, some set of constraints that can represent membership in the language, okay? So this was our recipe, And we kind of did this, several times. And so we could ask, look, what encodings did we use, for some assignment? In all cases, we had some assignment, right? It was maybe polynomial size or exponential size or whatever. We always had some assignment that we were encoding. Look, for exponential size PCPs, we used what, we didn't really call them like that. We can think about them as linear extensions, okay? And again, in this course, I don't really emphasize the coding theoretic perspective as much, but that is the Hadamard code. And intuitively, the encoding of A, okay, which has length n, was a function from f to the n to f, right? That the function itself consists of all these locations, okay? So if you give me an input C, the answer of the function is the inner product of A with C, okay? So that was what the encoding was. For polynomial size PCPs, we used multivariate low-degree extensions, which is also known as the Reedy-Muller code. And we kind of saw two different regimes of this encoding. One was with logarithmic number of variables, where the encoding was basically the multilinear extension of A. And then we also saw this other setting of parameters where the number of variables was kind of log over log log, right? And here this was like a just generic low-degree extension where now the side of the hypercube was maybe larger than 2, okay? And crucially, for A, we had the linearity test that made sure that sort of what the alleged encoding really belongs to the set of valid encodings. And for B, we had the multivariate low-degree test that made sure that whatever alleged encoding in this format was indeed, close to some valid encoding. And how did we test satisfiability? We used kind of different tools depending on so in the case of exponential size PCPs, we used random combinations and tensor tests. And primarily for low-degree extensions, we used basically sumchecks for basically everything. We just, whatever problem showed up, we always reduced it back to sumcheck. It was either 0 and subcube or input consistency, we always reduced them back to it. Now, curiously, there is a pattern of basically making the coding smaller and smaller. This first encoding that we saw was exponential. Then this other encoding that we saw was almost polynomial, kind of n to the log log n. And this final one that we saw was a polynomial, okay? And you could make it, as close, it was like n to the 1 plus order epsilon with a trade-off on h, right? The bigger h you made it, the closer it would get to linear. But you couldn't quite bring it to linear. So that's kind of the arc of encodings that we have seen so far. Are there questions about it? This is just like kind of recapping, where we've been. Okay. And as I explained last time, we kind of exhausted what we can expect out of multivariate low-degree extensions because they're not going to get us past this n to the 1 plus order of epsilon. Okay, if we want order of n, we're going to have to leave behind the multivariate low-degree extensions. But you see here, there's a pattern, right? As we have reduced the number of variables and we have increased the size of the hypercube, our encoding became sort of smaller and smaller, okay? And, kind of this should suggest in which direction we're going to go. Any questions about this slide? All right. So we're going to have to pick some new encoding. And, there's only so much we're going to be able to recycle now. And so the encoding that we want for linear length proofs needs to satisfy this kind of two basic properties. One is something you could call constant rate, that basically the encoding of an assignment should be no more than a constant the size of the assignment. That's a pretty tall order, okay? And also something that you could call constant relative distance, that if two code words have, if the distance between two words, let's say, actually, that's not what I wanted to say. If two assignments differ, even at one location, then we want the fraction of differences between the two corresponding code words to be some constant fraction. Okay? This is the main reason why we everywhere when we constructed PCPs, we took the field to be large enough, was so that we could have constant sumness error even when there was like a minute difference between two assignments that were differing at, say, even to one location, which can make the difference between satisfying and unsatisfying, and so that we could in principle even have a chance of telling the difference between the code words, never mind checking the satisfiability, right? That was kind of like a bare minimum requirement. And that's not all we need. We also need an encoding that is going to let us execute our recipe, which means that we need some proximity test, right? We're going to have to be able to say that when you give me some alleged encoding, is it close to some valid encoding, okay? It wasn't just enough to have some encoding. We always had to have a proximity test to go with it, like a linearity test or logicity test. And we also had to have some approach of testing satisfiability, like just the mere fact that a function that is written down by the prover is close to some valid encoding doesn't mean that I can conduct tests about what's encoded underneath. Okay, I need something to go with it. And when you put everything together, kind of the first two requirements are actually very easy. It's just basically any good code over a field. The real requirements that are making this choice of encoding rather restricted is really the other ones. And in general, we have very, very, very few types of encodings that let us support these things, okay? Nonetheless, and so like I want to say that sort of the scarcity of appropriate codes for doing this recipe is one of the main let's call it causes of frontiers in the probabilistic proof literature. If we could just dream up encodings that satisfy the properties that we want, we would have sort of probabilistic proofs with all the properties that we want in the world, right? So these are like very harsh requirements. Anyways, coming back to the prior slide with this pattern that as we reduce the number of variables, the encoding become more and more efficient. The encoding we're going to study today and start using is univariate logic extensions. Okay, so we're going to basically continue to place our hopes in polynomials. That's generally what you should be doing in this racket, because somehow they always work. But we haven't really tried to exploit sort of univariate logic extensions. And there's a reason for that, and we'll come to that in a moment. But let me just first clarify, what univariate extension means. So we've talked about logic extensions many times, including univariate ones. And here I just mean when you encode an assignment, you're just going to consider its logic extension evaluated over the field. Actually, I lied. We're actually going to not evaluate it over the field. We're going to evaluate it over some specific subset. We're going to call it L, some evaluation domain. And this evaluation domain is you should think about it as like a constant times larger of the assignment that we have. So we have some assignment over, let's say, of size 100. We're going to take logic extension and evaluate it over a domain of size 1,000. Okay, it's 10 times bigger. Why not choose it to be the field? Because that's kind of what we've done so far, right? Every time we took a multivariate logic extension, we evaluated it over f to the n, right? It was over the whole field hypercube, right? Why not evaluate the univariate extension over the sort of single field line as everywhere you can? There's a couple of reasons. One is that some will see logic tests that actually don't want to work with the whole field, but they want to work with highly structured specific sets. Okay, so we need this decoupling. All right. And the other one is that sometimes you really want the field to be larger because you want to do some work over the whole field, but you don't want to force your logic extensions to grow with the field. Okay. So, and in the setting of univariate logic extensions, which is made to kind of achieve this linear proof length rather than just some polynomial proof length, then this matters. Before we had sort of the granularity wasn't fine enough for us to care about where we evaluate specifically the logic extension. Okay? But so starting from now, think that logistic extensions come always with some evaluation domain. You start with some interpolation domain, H, and you evaluate over some other evaluation domain, L, that is like larger than it. This encoding has its own name, is known as the Reed-Solomon code. This is a set of valid encodings. Okay, these are all the functions that if you over the interpolation, so over the evaluation domain, that if you interpolate them, you get the right degree. And crucially, like the relative distance of this code is 1 minus degree over the size of the evaluation domain. Why? Because two polynomials of degree d can agree in at most d locations, and in the worst case, each of these d locations are precisely over the evaluation domain, and so you could lose up to d over L. So two code words in this code must differ in at least 1 minus d over L locations, and if L is order of d, then now we have constant relative distance. So this is telling us that if I take L to be on the order of H, then I will have an encoding that is sort of with constant rate and constant relative distance. So that's like a good starting point. But right now we have no idea whether we'll be able to do this. But as I had said, we're going to continue to place our hopes in polynomials, and so we hope that because we're working with polynomials like what we've been doing for weeks, then because of that we'll be able to somehow figure this out. Okay? And kind of the point of today's lecture and next couple of lectures is to basically show that yes, with enough effort you can actually sort this out. Okay? And pull this off. So for today specifically, we're going to temporarily assume that we have a proximity test for univariate extensions, and we'll basically try to figure out the rest. Okay? So we'll try to construct a linear length IOP, provided that we have some way to check that a arbitrary function over L is close to some function over this code, okay, to some univariate extension. This should sound like a big assumption, because when we talked about low-degree testing, we started out actually studying low-degree testing for univariate functions. And if you remember, I mentioned that to test that a function is close to the evaluation of a polynomial of degree d, you're going to need order of d variables. Otherwise, there's just no way you can test it. Okay? Because until you ask d plus 2 queries, you have no information about kind of what's going on. Like any answer you get could have been consistent with a degree d evaluation. So that's not good, because for us the degree is going to be pretty large, linear in the instance size. Okay? So somehow assuming that we have a proximity test seems awkward, given that we basically argued in a prior lecture that it's impossible to have a non-trivial low-degree test for univariate functions. The resolution that we'll see next lecture is that we can ask help from the prover, okay? And with help of the prover, we'll see that we can actually test, we can basically circumvent that impossibility or that barrier and test proximity to this code in logarithmic in D. So we'll kind of sort that out. So for now, sort of don't worry that we will be able to get a proximity test. It'll just be a proof-aided proximity test, okay? This is unlike the other tests we've seen in this course, linearity test and logarithmic test, where you just directly test the object without any help from the prover, right? All right, so we're about to get into like some concrete protocol building. Specifically, let's use univariate polynomials and build an IOP of linear size, assuming we can test things. Are there any questions? Okay, so either everything is clear or everything is definitely not clear. Can we get some nods from, I guess, the one person has a video? Okay, good. So for those of you without video, so Julius gets to kind of tell whether I continue or not. All right, So, okay. So what we're going to do is that we're just going to continue with our optimistic guessing. Okay, and of course this is premeditated guessing, so it's guessing up to a certain point, right? But basically we took a lot of mileage out of the multivariate sum check, right? We basically constructed on it PCP for NP, PCP for next, PCP for n time. We did so much with the multilinear sum check, multivariate sum check. Can we somehow come up with a univariate one? Maybe it will be just as useful. Hint, yes, it will be just as useful, but we need to first come up with it, right? So that's what we're going to do first. Okay, let's just kind of warm up and start using logic extensions somehow. So this is the problem we want to solve. The verifier has oracle access to a univariate function defined over the evaluation domain. And for now, we're just going to assume it has oracle access to the function in a way that the function already is guaranteed to have low degree. Now, eventually, we'll test it, but for now, it has low degree. It has explicit input f, l, d, h, gamma. What is this? Well, f is the field we're working over, the evaluation domain, so it knows what it is, the degree. And then sort of this h and gamma define a summation problem, a claim that the verifier needs to check, which is it indeed the case that f, when you sum it over h, you get gamma? Notice here that I have a hat here, right? And remember, in this class, hat means like you extend it, right? And you look at whenever I write the hat over a symbol, as we've done in other lectures, means take this thing, interpolate it, and whatever polynomial comes out, okay? Obviously here, the hat makes sense because I want to ask what is the degree of this function. The hat here also makes some sense because h and l, maybe they don't have to like completely coincide, right? And maybe h kind of overlaps partially with L, and so f is not defined necessarily over h. But once I interpolate it and evaluate it over h, then I can evaluate it wherever I want, right? So that's why this one has the hat. So the univariate sum check problem is to solve this problem, okay? With a protocol. So, and the main challenge here is that kind of everything here grows linear. You should think about it as growing linearly. And so this h, when we talked about hypercubes, was like a small quantity. Now it is the only thing that we have, so you should think of h as huge, okay? And also the degree of the function is huge. So the amount of information content in f is something that we cannot sort of expect to kind of read off. All right, so let's start with some really naive solutions just to kind of get situated. Let's say that I query f at every a and I just add up the answers, okay? Kind of like this trivial way of trying to solve the problem. So what goes wrong? Well, first, it could be that h and l are just disjoint, and so I can't just query f at every a in h. There's just no a in h in l, okay? And yet the f that is given to me is over l, right? And deriving f of a for a single a in h would require us to read off like all the information about f, interpolate and evaluate at a, right? That would be way too many queries because the degree is too large. We could do this if degrees were small, right? That would be like potentially a reasonable thing to do, but the degree is large, okay? Because f will be encoding an entire assignment for us. But even if h is in L, like size of h itself is large. So again, we're again having a problem. And even if h were small and the degree were small, in the noisy case, we would have to use somehow self-correction, which we don't have, right? Or at least we haven't seen how to do it, right? I said that we don't have a proximity test, never mind a self-corrector, okay? So just this naive way of just obtaining the values of f over h, f hat over h one by one is just like a very kind of, maybe it's almost confusing because it's a very straightforward idea. I just want to say that, this very straightforward idea doesn't work for a number of reasons. Some other attempt could be to say, all right, well, we have a multivariate sum check. Why can't just we run it on a single variable? So we just run the sum check protocol for this statement and n equals 1, right? And remember, we are in IOP, so we can even run it as an interactive proof. We don't even have to unroll it, right? So what would happen? Well, the first and only message in the sumcheck protocol would be the d+1 coefficients of f hat, right? The prover would just send us some coefficients. And what would the sumcheck protocol do? It would construct the polynomial, alleged, sort of represented by these coefficients, check it would have the right sum, and check that coincides with the oracle that I have access to at a random point. Okay? This is the multivariate sumcheck protocol when n equals 1. Okay? It's just basically the last round. And this is basically kind of, again, silly because we are receiving order of n information. If we were willing to receive this amount of information, we could have received the assignment to begin with. The way you see it is that receiving a message of this sort that is this big in an interactive proof is tantamount to having basically an enormous alphabet from which you're just reading in one symbol the entire assignment. Okay. So we need new ideas. Okay, so just silly idea number 1 doesn't work. Recycling the multivariate sumcheck doesn't work. So we're gonna have to do something else. Okay. Are there any questions about attempt 1 and attempt 2? Maybe they're a little bit too, I don't know, naive, but hopefully that clarifies that we can't recycle. I'm trying to get you recalibrated to the univariate world, right? H is big, D is big, okay? That was not the case in the multivariate world, right? We were happy to pay linearly in D and in H in the multivariate world, okay? All right, so please do ask questions if you have them. All right, so what are we going to do? So we're gonna basically try to use some algebra, okay? The first step is we're gonna try to understand what happens when we take a univariate polynomial and we sum it up, okay? And the first step, we're gonna try to basically reduce to the case where the degree is smaller than the size of the summation domain, okay? H is the summation domain. So let v sub h be the vanishing polynomial of the set H. We have already seen this type of polynomials multiple times. And if I divide f hat by v sub h, I obtain the quotient and the remainder, right? The remainder has degree strictly less than the dividend, right? And the quotient is whatever is left, right? Notice that if I write f hat this way, I might as well focus on g hat because they sum to the same quantity over h, right? Because if I sum up f hat over h, this term vanishes everywhere on h. Why? Because we have the vanishing polynomial of h, right? And the only term that affects the sum of f hat over h is its remainder upon division by the vanishing polynomial, okay? So somehow, like in some sense, all the hardness of the problem is in the remainder, okay? Intuitively. So are we fine with this? Now, I haven't written a protocol, we will write a protocol in the next slide. Here I'm just saying that if I want to understand f hat, I just try to basically see how it looks when divided by the vanishing polynomial of the summation domain, and I focus on the remainder because it's the only thing that will affect the sum. Okay? So let's focus on polynomials that satisfy this condition and see how do they behave on a set. Now, in general, I have no idea, okay? So we're gonna assume something. We're gonna assume that H is nice, okay, according to some notion of nice, and we're gonna rely on some algebraic properties. Notice that this is fair game because in the multivariate sumcheck, this summation domain was also nice. The multivariate sumcheck specifically works for product sets, right? It is h times h times h times h, or maybe, I don't know, h1 times h2 times h3, whatever. It's not just whatever subset of f to the n. It had some structure, and because it had this product structure, we could run a protocol, right? So similarly here, I'm gonna basically allow myself to impose some structure on the set H, okay? And given that it has structure, we're gonna make some observations that help us solve this problem. Okay? So we're not going to be solving it for arbitrary h, just like it is not solved for arbitrary subsets of f to the n in a multivariate world. And so here is a statement. We're going to let h be a subgroup of f star. Okay, so what is f star? F star is the multiplicative group of the field, right? You basically throw out 0 and you throw out also the addition operation. You just think about it as one big cyclic group. And let h be a subgroup of it. Okay, so that's the structure we're going to impose. And we're going to prove that if you take the sum of g hat, or really any polynomial whose degree is strictly less than the summation domain, then what you're going to get is h times the constant term. Always. Doesn't matter what the polynomial is doing. Like you sum a polynomial of low degree over a summation domain, and the summation domain is a subgroup, then you always get h times the constant term. This is actually a two-line proof. It's very straightforward proof. Let's first consider a monomial, okay? Because anyways, a polynomial is a sum of monomials that are sort of weighted. So let's say that g hat for a moment is just x to the I. So that means that we're looking at summation of a to the I. Now, because h is a subgroup of f star, and f star is cyclic, I can actually rewrite the elements of A as just some generator of h to the j, okay, from 0 to h minus 1. Now, if you flip the indices, that's what I get. And now there's only two things, right? So I'm summing up basically all the roots of unity if I is not 0 mod h, right? Otherwise, I'm just summing up 1 h times, right? And it's kind of the picture you should have in mind is that, for example, at least over the complex numbers, all the roots, if you consider the sum of all the roots of unity, they always balance each other out exactly, right? So, for example, if you look at the fifth roots of unity, is that it? Yes. They're all kind of equally spaced on the unit circle. If you add them all up, you get 0, okay? Whenever you add up all the roots of unity, you always get 0, okay? And so that's the picture you should have in mind. So this is telling us that all monomials with a positive power just sum to 0, and you're left with the constant term h times. Okay? So that's it. When you take a polynomial of degree strictly less than h, the only term that survives is g0, which is a constant term, h times, right? Any questions about this statement? Anyway, well, so what? Well, in the meantime, we have a condition that this thing sums to gamma if and only if the constant term is gamma divided by h, right? So basically, now we have learned something. If I'm trying to understand this problem, really, I only need to understand how the remainder behaves. And how does the remainder behave? I only need to understand the constant term of the remainder. Okay? That's all we've learned in this slide. Okay? For univariate polynomials summed over the sum multiplicative subgroup, if I want to convince you that it has a certain sum, I need to convince you that the constant term of the remainder is something. Okay? That is my goal. That is my way of telling you the sum is this much, right? Let me just pause for a moment. Are we together? Yeah, I haven't used any deep facts, okay? So we use the GCD algorithm here, right? And just roots of unity sum to 0. That's all really, okay? You may ask what happens in the case of additive subgroups. Something similar happens. Instead of being the lowest order term, it is the highest order term. And proving it's just a little bit more awkward. So that basically any subgroup of f, whether additive or multiplicative, will satisfy some nice property. So it's a nice open question whether other nice subsets of f have properties like these. Questions about this slide? Because we're about to build a protocol for univariate sumcheck, and it's important that if there's something not clear here, then you sort of bring it up now. Don't be shy. Okay, so nobody speaks. It means everything is clear. Yeah, go ahead.
You have to be a little careful about when you're doing this now. Do you have to be more careful of taking your field size just to make sure that you have a large enough subgroup of F star?
So the question is, in order for me to do this, I need to make sure that I have F star is large enough. Yeah. So in general, even when I write statements like these, right, the degree of F hat is at most D. I'm already assuming that D fits inside the field. Otherwise, I wouldn't write D here, right? So we know that F is going to be definitely at least the size of at least D, right? And generally D will be actually larger than H, okay? So here the dominant term in this entire slide is D, okay? And
sorry, but like the point is, like, as long as F star is like at least twice as large as the H you want, you should be good, right?
As long as F star is twice, why twice?
Then you would have a subgroup of order like F star over 2.
But why do I want specifically?
F star has P minus 1 elements, right?
Yeah.
For some large prime.
Yeah.
And so you have some subgroup of size P minus 1 over 2. Are you using this like the yeah, maybe I'm confused here.
So I agree that sort of F star, is let's call it Q minus 1, right? So maybe it's a prime field, maybe it's not, but it's going to be some prime power minus 1, right? We're going to need this thing, let's say, to be greater than D, right? Sorry, let me just step back for a moment. We have already assumed that size of F is greater than D, right? And F star is Q minus 1, which means that this is divisible by H, right? Because otherwise we wouldn't have a subgroup of that size. Now, what specifically is H? It actually doesn't matter right now for this slide, okay? I can, everything I've written so far holds as long as, basic things make sense. Namely, the subgroup has the right size, which means has an allowable size, which means that it divides the order of F star, and that the degree sort of fits inside the field. I don't think I'm using anything else here.
Okay.
In particular, you could have H being small relative to D, or you could have already H being larger than D, in which case the quotient here would be 0. Okay? So either of those are fine. The general regime in which we will be invoking these facts is that you should think of D as something like 2 or 3 times the size of H. So we'll generally be using the step 1 non-trivially. And then I will reduce you back to this case. Good question. More questions? Okay. So now we have these facts which seem curiosities at best, but now we will leverage them to construct a polynomial, because a protocol, because these curiosities actually give us some pretty concrete statements we would like to convince the verifier of. Okay, so now we're going to see a protocol for a univariate sumcheck. It's actually not even an IOP. It's like completely non-interactive, so it's something we could have done in PCP world as well. And so the prover will compute this H hat and P hat. What is P hat? Well, in the prior slide, our G hat was this one, right? In the prior slide. But remember that we wanted to show something particular about the constant term of G hat, right? So what we're doing here is I'm asking the prover to not send me G hat, but rather something related to it, which is all the non-constant part of the polynomial, taking out x. Okay? Right? Because if I'm looking at all the powers, x squared, blah, 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 I can always pull out x and I will get some polynomial, right? And so we have this expression, okay? The constant term is gamma over h. Why? Because if you take h times the constant term, you get gamma, and gamma is the claimed sum, right? So anything that looks like this must sum to gamma, okay? So if anything looks like this must sum to gamma, okay, please tell me kind of the decomposition of f that represents, this identity, right? And what will the verifier do? Well, the verifier will just test that h and p are close to their corresponding degrees, which is I think that should be, seems to be h minus 2 there, sorry. D minus h and h minus 2, right? Because g was h minus 1, and so if we remove x, that's h minus 2. And it will test this identity at a random point. Okay? So we're about to analyze this, but I hope the intuition is clear. This identity captures the property of summing to gamma over h. And I already have f, I'm missing h, and I'm missing p, right? So I asked the prover, please give them to me. And I already know gamma, I already know the size of h, I already know the vanishing polynomial. I just kind of complete the rest myself. And that's, that's one query to f, one query to h, one query to p at the random location s, okay? And this is what I'm going to check. All right, so let's analyze this protocol. Well, if the claim is true, then the prover can write things this way, can send functions that really are low degree so that this test passes. And because this identity holds, this test at a random point in L also will pass with probability 1. Are we all in agreement? Okay, so the question is what happens in the bad case, okay? So suppose f hat doesn't sum to gamma, okay? Then we have two cases. Either the prover is silly enough to send me some functions that are far from low degree. I mean, that is an option. He can do that. That's not very smart. Or they are close to it, and then it will hope for the best for this other test, right? So let's see what happens in either case. So in the case of one, the low degree test that for now we have assumed will just accept with some probability that is related to this delta far. And you should think of delta as something like 1 over 10 or 1 over 100. Let's say that they're 1 over 100 far. That means that the probability the test accepts will be at most some function of 1 over 100. Okay, so maybe it will accept with probability at most, I don't know, 75% or like 80%. Okay, something like that. So that's like really a pretty silly strategy. Anyways, the protocol is sound, so there are no smart strategies, but let's see the less obvious one. So if they're both close to some, in this case, unique h and p, because we're going to pick delta to be small enough so that there is only one closest polynomial, then we know that whatever these h and p are, okay, this cannot hold as an identity. Why? Because if there exists any h and p for which this identity holds, f hat sums to gamma. But we have assumed that f hat doesn't sum to gamma, so there exists no h and no p that make that identity hold. So whatever these guys are, this identity cannot hold. Okay? Well, if it cannot hold, now the probability that this step passes is at most a probability that sort of the two polynomials, the left-hand side and right-hand side, happen to agree, but that can happen at most in d over L points. But that's not everything, right? There's also some noise, right? Because we are accessing noisy versions of the polynomials. So we're querying h and we're querying p. Each time we could be racking up a delta probability of just landing in a bad place, and then God knows what happens, right? Now, eventually, we also have to take into account the noise of f, but right now I'm assuming f is exactly low degree, but the fact that f is queried at a uniform random location is important, okay? So eventually there will be like a third, 3 delta here, okay? But is it clear? We have basically, all we've done is we have reduced summation over h to gamma to a polynomial identity test. Once we have it, we ask the prover to send me the auxiliary polynomials so I can run the test. And that's it, okay? And even though it doesn't look very much like the normal sum check you're used to, this is, a problem for solving sum check. Now, of course, we haven't talked about how to test the things are close, but we'll see that next time. Any questions about this univariate sum check? So we are about to incorporate this into more protocols, and so it's good to be clear about it now. Okay, notice that crucially, the amount of information sent from the prover to the verifier is linear. Okay, we're not doing like an efficiency analysis on every slide. We'll do it at the very end with the full protocol. But notice that so far, at least we are within budget. Okay, we're making a small number of queries, and whatever the prover is sending is within budget. Some two times the size of L, right? Okay, that's it for univariate sum check. So we're going to have to construct a protocol for R1CS. Now, R1CS has these matrices ABC that you need to multiply by a vector. So let's do like a brief warm-up of just checking linear equations first. Okay? This will be like a good warm-up. So here's the problem we want to solve. You give me oracle access to 2 functions defined over L of both of degree, let's say at most D. And I'm given this explicit input. The main difference is that this time the problem is described by a matrix, okay? And what does it say? It says that if you take f hat and you evaluate it over h, you multiply it by the matrix M, which is h by h, you're going to get some other vector over h, and that should equal to g hat evaluated over h, okay? So that's a problem we could check, okay? Is it clear? So this is matrix times vector equals a vector, okay? And the respective vectors are, when you take these guys, you interpolate and you evaluate over the, in this case, the domain H, okay? Are we comfortable with the problem that we want to solve? Notice that, again, I have access to these 2 oracles and I want to argue, please convince me with some help that without making too many queries to f and g, I need to establish that this relation holds, okay? Notice that again, this is a relation that is pretty large, right? So matrix times vector equals vector. It means that, each of h conditions here is itself a vector of size h times a vector size h, right? So this is like a pretty large, I can't just go and ask all these questions individually, right? So it's a large problem to solve. There's many conditions and involve many variables. But the idea is that now we have a univariate sum check. Remember that when we had a multivariate sum check, we could solve everything under the sun. We just had to be careful about how we're using to it, okay? And that's basically still the case now for univariate things. If we have a univariate sum check, we can basically solve any problem we want, okay? So what we're going to try to do is we're going to take this problem and massage it and turn it into a sum check problem, and then we're going to run the sum check protocol to solve it for us, okay? And the way we're going to massage this problem into that is going to be very, very, very similar to things that we have done a million times already in the multivariate case, okay? So, all right, so what does this mean? Well, that's just a bunch of conditions. Here they are, right? Every location of g hat on H should be a specific row times, all of f, okay, on H. So these are these are all the constraints that we want to check, right? I can rewrite this as the coefficients of some univariate polynomial, okay? And what is this int of a? It's just some bijection from h to 0, 1 through h minus 1, okay? So I can take all of the constraints I care about and I stash them as the coefficients of some polynomial. And they hold if and only if this polynomial is the zero polynomial, right? Because if one constraint doesn't hold, then it means that this is not the zero polynomial, okay? Again, we've done this like a million times already, okay? All right, this starts looking closer to like a sumcheck problem. Specifically, let's say that we evaluate the polynomial at a random r, okay? So let's fix some r, and I can express this quantity at r as something like this. Basically, I just pull out by itself kind of this one, right? That's this part over here, okay? Now, what about this other part here? I'm kind of re-indexing things here, right? Because what am I going to get? So this other part here, it seems like f hat is indexed by b, whereas here it's indexed by a. That's fine. I can just rename a and b. That's okay. And I'm just basically transposing the matrix. Okay? So basically, you know, for any given, you can split this into two sums and just like re-index things, and that will kind of transpose the matrix. Okay, so notice that here it's sum over b, mba, right? This instead is sum over b, mab. Okay? But, you know, nonetheless, now we have this sum over a, and what I can do is I can just take this entire mess here and call it a function. That function is something that depends on m. Okay? And why do I put a hat on these guys? Why do I put a hat on these guys? Because I want to apply the univariate sumcheck. Univariate sumcheck wants the addend to be a polynomial. So we're going to extend the randomness into its corresponding logarithmic extension. Here is just pure randomness, the powers of r. Here is like the powers of r sort of mixed by the matrix M, okay, and then extended. Again, we've done this before. In fact, we have already mixed things. In our first proof of NP has polynomial size PCPs, we actually extended the sort of randomness times the coefficients that were kind of reordered. Okay, we kind of already did this once before. But okay, so now I have some expression that I can plug into the sumcheck. This is some polynomial of degree d plus h minus 1, right? Because the logarithmic extension of the randomness has degree strictly less than h, at most h minus 1. And I start with f and g, we have degree at most d. Okay, so this entire thing is something of low degree, d plus h minus 1. All right? So now I can come up with the protocol. The verifier sends randomness, and then we solve this sumcheck problem. How do we solve the sumcheck problem? Well, you know, we run the protocol from the prior slide. At some point, the subroutine is going to want to query this addend at S. We query f and g at S to get the answer here, right? And I'm going to evaluate myself this one and this one at S, okay? Which costs me order of h plus order of plus, you know, size of m operations, okay? Okay, let's just check if we're together. What is the soundness error of this protocol? Let's start, you know, for example, from this randomness here. Like, what is the error in the choice of R? Like, there's some bad choices of R, right? So what is the largest, so it should probably be related to the degree of this polynomial, right? So what is the largest degree of this polynomial here?
Size of h minus 1.
Right, size of h minus 1, right? And by the polynomial identity lemma, we know that a polynomial of degree d has at most d zeros, right? So the probability that I get, you know, this being summing to 0 even though the polynomial that we started with was non-zero, is at most h minus 1 over the domain the size of the domain from which I selected R. R is just a random field element, so I get h minus 1 over f plus, whatever is the soundness error of the univariate sumcheck underneath, right? And again, in the actual application, maybe f and g are noisy, and I have to take that into account as well. And it's important that I'm querying them not at a fixed location, but some random location. We'll see everything come together in the next slide. But basically, now we have co-opted the univariate sumcheck to help us check linear relations between oracles. Okay? All right, next slide is going to be a full slide. I guess this slide is also full, but the next slide, we're going to build up the protocol for R1CS. And we have put together all the components we need. Any questions before we get there? Okay, so now we're going to put together the protocol. So we have the prover and the verifier. The prover and verifier each receive an instance, which is some explicit input U, and 3 coefficient matrices ABC. And the prover additionally receives some witness W. Okay? So first thing the prover does, it just assembles the full assignment by just putting together the explicit input and the sort of auxiliary input W. Now you have this full assignment over the whole space. So in this protocol, there's going to be one new idea that we haven't seen before, because it is specifically about R1CS, is that we're going to have to somehow deal with the explicit input. This already came up in prior protocols. For example, in the protocol for end time, we had to somehow deal with explicit input. Okay? So specifically, we're going to think of H as being made up in 2 parts. The part where U lives, let's call it H in, right? And the part where W lives, let's call it H aux. Okay? And we're going to ask the prover to basically take the witness, which is defined over H aux, and kind of shift it by some magical term. We'll justify the magical term in a moment, but basically W prime is just a shifted version of W, okay? And we'll see in a moment kind of what is this magical shift. But the main point is we're going to ask the prover to give us the extension of the shifted witness, not just the witness on its own. Notice that I didn't ask him to give him Z. The intuition is that the verifier is going to augment this one itself on the fly. Okay, it's going to construct f of Z on the fly from FW. Okay, we'll see that in a moment. So come back to that in a moment. I just want to first see all the things that the prover sends. The prover also needs to kind of send me all the linear combinations, right? So it's going to take the full assignment Z, multiply it by M, extend it and evaluate it over L, right? And that's going to be some matrix I'm going to call FM, all right? So these are the 3 linear combinations. And then it's going to send me, we've seen these type of things before. It has to prove to me that the linear combinations like agree entry-wise, right? Entry-wise over H. Well, that's the same thing as vanishing everywhere on H. Okay, and that's why I divide out the vanishing polynomial of H. And you give me the quotient. And I take all these things and boom, I send them off. 1, 2, 3, 4, 5. 5 oracles sent to the verifier. Okay, that's 5L. Okay, so we're still within budget. So first, now we're going to dispel the myth of, why did we shift the witness this way? Because the verifier is going to think on the fly some sort of virtual oracle constructed from the actually received oracle and the thing it actually has. The verifier has the explicit input U, so it is free to extend it himself, right? So I'm going to construct this F, and I claim that in the honest case, this is an extension of Z. Why? Well, when A is in H in, this term falls off, and all we have is what the verifier wants, right? When A is in H aux, well, this time is not going to vanish. It's going to cancel this term, right? And then this thing is going to be cancelled by this one, we're going to be left with the actual witness. Okay? So this is basically on-the-fly extension, okay, where the verifier supplies the part it knows is correct. Okay? So that's why we shifted this witness this way. This is just in the verifier's head. Okay? Now, the verifier needs to check a variety of things. So it's going to check this polynomial identity to make sure, intuitively, that the polynomials that underlie fa, fp, and fc agree on h. Okay? That was this identity here just shifted around. But then we also need to make sure that the linear combinations are correct. So what are we going to do? The verifier is going to send some randomness, and the prover is going to compute this sumcheck expression. So now I'm peeling off the layers of abstraction so that you see kind of what's happening underneath. So remember, in the sumcheck protocol, on the left-hand side, we had the summand. Okay? What do we have in the left-hand side in the case of linear equations? Well, we have r hat, mz hat, that is the thing that is supposed to be the linear equation, sorry, the linear combination. Then we have the linearly combined randomness and the thing being transformed by the matrix, right? So this is the left-hand side of the sumcheck, which is that expression that we derived for checking linear equations. On the right-hand side, we have the expression for sumcheck. Well, I'm not sure there's a minus here, it should be plus. And notice that we also had before plus gamma over h, but gamma is 0, so this is not here, right? So it creates this gm hat and hm hat, one for each sumcheck, and we are basically running univariate sumcheck for this one. You know, this is just like a semantic sort of a description. What's actually happening is I get these oracles, okay? So I get 6 oracles, 2 oracles for each m. Each 2 oracles are going to prove that this is the right linear combination of f, okay? And this is the right linear combination of f, this is the right linear combination of f, okay? So now I have to check these polynomial identities as well. So here I am doing that, okay? By the way, here the color coding is that green are queries and red are things that I compute myself, including this one, by the way, right? And I guess this f here should be like partially green and partially red because, you know, the definition of f inside it has an oracle that I received and the rest is computation that I do, right? And after I do this, I just test everything, that I make sure it's the right degrees, you know, kind of wrote them out here. And I make sure those are the right degrees, okay? And this is the protocol. We're about to do the soundness analysis, okay? I want you to notice that we have sent 11 oracles in total, 5 plus 6, so that's like 11 size of L. So that is a linear proof length, okay? And the verifier just sent like a randomness going back, okay? And we only have 2 rounds. Now, of course, we have the test also, but again, today the test is, we're gonna ignore it, we're gonna see it next time because it is its own beast. Is the intuition for this protocol clear? Okay, so let me just I want to make sure that this part is clear. So the verifier is curious whether this is the case, right? But the prover sends something that is allegedly the linear combinations, plus the verifier needs to check that they really are the linear combinations, right? So this condition is equivalent to this condition, these 4 conditions, right? And these 4 conditions are precisely, let's call them 1, right? That's this one checked here, right? And this 2, 3, 4, right? They are like, you know, 2, 3, 4, right? They're being checked there. So we have these 4 subconditions that imply the main sort of R1CS condition. and the input consistency is just handled on the fly. Okay? Right, so this is the protocol. So now we're gonna have one slide just to look at the soundness analysis, but we already proved it in some sense, right? All the components, we already argued it. So also, by the way, like I don't really need to run 3 sum checks because it's a linear relation. I could send coefficients and merge them all into one sum check, and I would just pick up an extra, I don't know, 1/f error term, which is not bad. So I don't really need to run 3 sum checks. All right, so I made the protocol small. Maybe you can read it, maybe you can't, but I need some space for the rest. But at least the protocol is roughly there. So suppose the instance we have is not satisfiable. If any of the sent functions is delta var, then we're done. Okay. So let's suppose that all the sent functions are delta close. So let these things be the 11 oracles closest to whatever is sent. They're unique because we picked delta small enough. Notice also that the last 6 ones here, did B also get a hat? That's not good. B is not extended. So, notice that these guys are also a function of R. These are like in the first round, these are the second round. Okay? So one of the following must be true, right? So either the Hadamard product condition is violated, right? So this doesn't hold. Or one of the linear conditions is violated. Why? Because this is not in the language, so for any polynomials we write down, one of these 4 conditions must not hold, right? In case 1, well, we're checking it here, right? So the verifier will accept at most probability degree of the identity over the domain over which I'm sampling from, and I have this 4 delta here. Why? Because I'm querying 4 oracles and they're delta noisy. Okay? So either I land up on the noise or I land on the polynomial itself, in which case, I still accept only if it's one of the places where these agree. Well, these space agree. And again, this 2h minus 1, 2h minus 2 is because we have h minus 1 plus h minus 1. This doesn't matter, and so we have 2h minus 2. In case 2, well, we have a randomized reduction, right? So there's some error, but except with small error, in fact, it's very small, it's over f, not even over L, we have some identity which doesn't hold, right? Because we get some sumcheck problem which is not true. But in that case, then we're checking that identity. And again, we pay 1, 2, 3, 4 deltas, okay? And the degree of the expression over L. And that's it. And again, so the input consistency is handled on the fly. There's a couple of subtleties here. I mean, one subtlety is that you need to make sure that this extending the input on the fly doesn't mess up distance, okay? But because I'm transforming it with polynomials, then it doesn't mess up distance, okay? So really, kind of f that is created is something that is delta close and necessarily agrees with the input. That is the soundness analysis, okay? And now we just need some bookkeeping just to kind of look at the efficiency. What are we communicating? Well, is order of L plus whatever the logic test needs. We'll see that next time, right? I'm telling you it will be linear, so it's order of n. The query complexity is just constant plus whatever the test needs. Next time we'll see it's logarithmic. Run complexity is constant plus whatever the test needs. We'll see next time it is logarithmic. Randomness complexity, again, logarithmic. Prover time, it is all these operations, you can just do them in L log L using FFTs, plus whatever the logarithmic test needs. Actually, logarithmic test is even linear, so it's dominated by whatever's happening here. The test is like a linear procedure. And the verifier time is linear. That's not exactly true. It also needs to depend on the number of non-zero entries in A, B, and C, which potentially is more than n. But because it has to apply the matrices to the randomness. But this is not something that affects anything else, just the verifier time. By the way, the verifier time is not sublinear, but that's okay because this is not a succinct problem. So what are you going to do? You have to read the matrices. So this is kind of optimal, right? And so this is what we got. This is a theorem, okay? We showed that R1CS has linear size proofs. The prover is in fact quasi-linear time. The verifier has optimal proof time, optimal time complexity. The fact that the field has to be large, we already used it because we're using this univariate extensions that forces us to work over large fields. This smoothness business, we kind of used it from we didn't really use it for the sumcheck. I mean, for the sumcheck, we just picked a subgroup, but we didn't say it was smooth. We'll see next time that we're going to need F to have subsets, specifically L is going to need to be smooth, okay? We're going to need that next time. So we are left to construct a univariate LDT with logarithmically many queries, okay? And because we're looking at univariate functions, we're going to need the prover to help us out because otherwise we can't expect to do less than D, but we want to do log D, okay? Okay, so this is a good time for me to stop the recording.